All right. Well, it's my great pleasure to welcome Nina Filippova from the University of Texas at Austin, where she works with Stella Offner. And even though Nina is still a graduate student, she already has things that you can say about her. She's a prestigious Department of Energy graduate fellow. And she's going to talk to us today about some of her exciting work on star formation with non-ideal MHD. So, take it away, Nina.
Thank you for the introduction. Yeah, so this is going to be a talk about the work I've been doing for the past couple of years, trying to simulate protostellar disks in simulations of not just single star formation, but really like multiple star formations, where like all these like interactions between different stars also may play a role in the formation and evolution of protostellar disks. And just to give credit for the background image here, this is from some simulations, part of the STARFORGE collaboration, which really explores star formation. Very beautiful images, so they end up in a lot of talks. Cool. So just to give an overview of the talk, I'll begin with an introduction. Just going over like what are protostellar disks, how do they form, and what is this magnetic braking catastrophe that shows up in theoretical studies of disk formation. A note on terminology. I know there's like, protostellar disks, circumstellar disks, protoplanetary disks. This work is focusing on like the first, like, maybe like class 0, class 1 stages of protostar evolution. So I'm just going to be using the term protostellar disks. And then also, so how do we model star formation and disk formation in numerical simulations? And how do we move beyond these like simple spherical models, which generally form a single protostar, to like these more complex interacting systems? I'll go over the numerical methods used for this work as a combination of GIZMO, the MHD code, plus some other numerical frameworks, which the aim of which is to give a realistic picture of star formation. I'll go over the results, which is the first calculations of multiple star formation, which model protostellar disk formation with non-ideal magnetohydrodynamics, which I will go into detail, and including protostellar jet feedback and radiative feedback from our protostars, and a little bit about future work. So protostellar disks, we have observed them around hundreds of nearby protostars. We know they should form frequently. The image on the left here is kind of like an artist's depiction of like what the structure is. You have a envelope of dusty material, like a disk forming around your central protostar. Usually there's also these like highly collimated bipolar outflows, the jets that I'll talk about later. On the right here, this is an image from the eDisk survey, which is aiming to find evidence of like planet formation in early like class 0, class 1 disks. Just kind of gives a sense of what we observe, how we observe protostellar disks, some typical sizes maybe. And we care about protostellar disk formation because disk formation and the evolution of disk properties affects things like the protostellar accretion rate. Most of the accretion happens through the disk. There's also the question of stellar multiplicity. How do we form multiple systems? There's an idea that these disks might become gravitationally unstable and fragment to form companion stars. And also, of course, we're interested in like eventually planet formation. And so, maybe different properties of like what's the dust content of the disk, the chemistry going on that has implications for what kind of planets might be able to form. So we know that protostellar disks should form from some pretty simple physical arguments, mostly just due to angular momentum conservation. So if we have like this, roughly spherical blob of gas floating around, we can get an estimate of like what like a typical protostellar disk size should be just by considering some of these simple arguments. So if we have like roughly like a 1 solar mass core at a typical temperature of like 10, 20 Kelvin, we can estimate like a radius, a Jeans radius, under which it'll start undergoing gravitational collapse of about like 0.1 parsecs. And from observations, we can get some like typical estimates of the rotational velocity of such cores, 10 to the minus 14, 10 to the minus 13 per second. And so the core will undergo gravitational collapse and the rotating gas will reach centrifugal equilibrium. And so material will start piling up at this like centrifugal radius, forming a protostellar disk. And so by appealing to angular momentum conservation, we can estimate the disk radius by like setting the initial specific angular momentum equal to the final specific angular momentum of like a fluid cell, and get like a typical estimate of like, 10 to like 100 to 10,000 AU, which is somewhat larger than observed protostellar disks, but within the ballpark. But this is again a pretty simple model, and we're missing some important physics. One of the most important ingredients is which is magnetic fields. And we know that magnetic fields are prevalent in the ISM from observations. We can measure some like typical field strengths, so 10 to 100 microgauss. And as these like images of dust polarization, which traces the magnetic field structure from the Planck collaboration, we can also see that there's like these fields tend to be well ordered on large like molecular cloud scales. So how do these magnetic fields affect disk formation? Again, so we're assuming that these are like well ordered on large scales. So a good approximation is to assume like a uniform magnetic field threading through the cloud. Even though we're talking about molecular clouds, there's still like charged species, ions, electrons, charged dust grains present in the cloud, and these become coupled to the magnetic field dynamics. So since I'll be talking about like ideal and non-ideal MHD later on, so in the ideal MHD approximation, you're assuming basically like a very like well-conducting fluid, there's negligible resistivities, and so the magnetic field and the gas dynamics become very well coupled. There's also like a flux freezing theorem, which basically states that like the magnetic flux passing through like a fluid bundle doesn't change. So again, the gas and the field motions are well coupled. And so what happens when you start forming a disk is that like as the collapsing material starts to rotate, this rotation drags the magnetic field lines. And the magnetic field lines resist this deformation. This creates like a magnetic tension force and torque. And so this like magnetic braking torque very efficiently actually removes angular momentum from rotating material. And you can get some estimates like considering this, like comparing the like magnetic braking time scale to like some typical rotation time scales. And like for even very moderate magnetic field strengths, you see that disk formation should be suppressed. And this is a problem because again, from observations, we know that disks form and also that magnetic fields are dynamically relevant in the interstellar medium. So coming from like analytic and like theoretical arguments, there have been like a number of possible resolutions suggested for the magnetic braking catastrophe. One of which is to, instead of considering like, you know, the rotation axis and the mean field direction being aligned, you could add some misalignment. Generally, magnetic braking is less efficient in the perpendicular direction. You could also consider adding some turbulence to your cloud. Then we might have some turbulent magnetic reconnection, which would diffuse the magnetic field lines and kind of smooth out the bending. And what this work really focuses on, although the other two components do play a role, is considering non-ideal magnetohydrodynamics. And so again, this is, instead of assuming a perfectly conducting fluid, now you introduce these high magnetic resistivities, which again can reduce the efficiency of magnetic braking. But again, these are pretty simple models, like considering like this like spherical cloud forming a single star. And this is an approach that was pioneered like many decades ago at this point by Larson, where you assume like an isothermal sphere, which collapses under its own self-gravity, forming a single protostar. But while this approach is nice because it's easy to like check the effects of varying different parameters, like, you know, comparing different magnetic field strengths or rotation rates, it's still not, it's kind of simplistic and it's not capturing like all of the dynamics that we care about here. And when we're constructing these numerical simulations, again, we can kind of look toward observed molecular clouds to kind of get a sense of like, you know, what are the necessary ingredients that we want to include in our numerical models, and what kind of like observations do we want to reproduce. So here we have an image of the 12CO column density map of the torus molecular cloud. It's an indication of some scales here. And so these molecular clouds and star forming regions, they're highly dynamic. There's an interplay of like gravity, turbulence, magnetic fields, stellar feedback. Here again, we're looking at the same cloud, but just again showing the magnetic field structure through the cloud. And so with all of these like competing forces, we have shocks, turbulent compression, and gravitational fragmentation, all of which promote structure formation. So we can look at this filament, we can zoom in, and like within the filament, we see some like dense, probably like at some point star forming cores, and so on and so on. So there's like the whole hierarchy of structure. And so essentially these like cores, they're not isolated at all. We also have a number of important stellar feedback mechanisms, and such as just like radiation from your star, protostellar jets, winds, and supernovae, and these all inject energy, momentum, and mass back into the interstellar medium. Protostellar jets, which I will talk about more in this work, are particularly relevant for low mass star formation, mainly because the stellar winds and supernovae are like associated with larger stars than what we are forming in these simulations. So again, these protostellar jets are an important feedback mechanism, and specifically there are these highly collimated, high velocity, like 10 to 100 kilometer per second bipolar outflows. The exact mechanism by which they're launched isn't still fully understood, but it seems to involve the interaction between the accreting material and like the wound up magnetic field lines in the protostellar core. And so here we have an image, a recent image with JWST, Big Arrow 211. And so this is one of the closest, most densely embedded like examples of a protostellar jet that we've seen. And so these jets, they're important because they drive turbulence on smaller scales within the cloud. They have been shown to reduce accretion rates and disrupt accretion flows in numerical simulations. So leads to an overall reduction in the star formation efficiency. And this is a figure from one of the papers in the STARFORGE collaboration, which examined the effects of different like feedback mechanisms on the shape of the initial mass function. And so this paper showed that like considering models with protostellar jet feedback versus without jet feedback, changes the shape of the initial mass function, leading to like a turnover at like lower mass scales, which is more consistent with what we observe. We also know from observations that stars often form in gravitationally bound multiple systems. And generally, we see that the stellar multiplicity increases with stellar mass. So our sun is a single system, but we see that generally for solar mass stars, like roughly half of them are found in multiple systems. And it's plausible to think that, you know, dynamical interactions between stellar neighbors or maybe, yes, other companions can affect disk formation and evolution. So we would like our, you know, we would like our numerical model not to just form single stars, but these actual like stellar systems. And also relevant to disk formation. So we know that most stars form in multiples, but the origin of stellar multiplicity still isn't fully understood. And there have been a number of like suggested formation mechanisms, for example, like fragmentation of filaments and cores, but also perhaps like fragmentation of a gravitationally like unstable disk itself. So one of the things we were interested in seeing in this work was like if we form protostellar disks, like do they end up fragmenting? Again, so star formation does not proceed in isolation. So these isolated spherical collapse models, they'll fail to capture like a lot of these dynamical interactions. There's growing evidence for things like asymmetric cores, these like large scale accretion streamers, like extending out to like tens of thousands of AU. And, you know, it seems that they can impact on the disk, they can provide additional material. There's also some interesting work on seeing how this like the accretion shocks from these streamers might affect like disk chemistry. There's also the possibility of like late stage gas infall where the disk forms not just from like the surrounding natal envelope, but from gas which appears at later times. And also this idea of like flyby interactions where there's some works that suggests that you know, for like typical like disk hosting stars, like roughly like half of them will experience an interaction within like 1,000 AU of like another companion. And these works also have some interesting consequences for disk behavior where like, for example, sometimes these flyby interactions can lead to like the secondary stealing like a large amount of disk material from the primary, even if like the secondary that's flying by has a lower mass. So again, we would like to include some of these like asymmetric and dynamical features in our models as well to get like a full sense of, yeah, like how does this affect disk formation and evolution. And finally, we probably would like to include non-ideal magnetohydrodynamics in our work because again, as the name suggests, molecular clouds are really only partially ionized. So there's like some estimates of an ionization fraction ranging from like 10 to the -4, maybe like the cloud boundary, down to like 10 to the -10 to the -9, or even like lower in the densest cores. And so we need to consider the effect of like collisions and relative drift between these different charged species that are present in our fluid. So in the ideal MHD case, we have the magnetic induction equation, which is describing the evolution of the magnetic field as quite simple. But once we consider like the non-ideal terms, these are typically parameterized in like astrophysical context as like the ohmic resistivity A to O, the Hall effect resistivity A to H, and the ambipolar diffusion resistivity like A to A. And so these non-ideal resistivities, they, which one is most dynamically important is a function of like the magnetization and the overall density regime that you're interested in. But within protostellar disks at like typical disk densities, all three of these effects are like expected to be important at some point. So specifically like ohmic resistivity is like electron and ion neutral drift or like collisions with electrons. And this is generally most relevant at like the most densest regimes. The Hall effect is like an ion electron drift, and this is a particularly interesting effect because the Hall resistivity can be positive or negative. So there's some interesting studies of like different behavior depending on like whether like the magnetic field is like aligned or anti-aligned with the rotation axis, some suggestions of maybe like potential bimodality of disk properties with the Hall effect. And then ambipolar diffusion, which is expected to be like more relevant in the low density, highly magnetized like surrounding gas. And so in general, these coefficients, they're a function of like the gas density, temperature, magnetization, and like number density and properties of your like charged species. J indicates, like the different charged species present. So yeah, to summarize kind of like what we know from all these observations, like what are like the necessary ingredients we would like to include in our disk models? We would want to have initial and boundary conditions representative of these turbulent magnetized molecular clouds. Instead of assuming like simple like isothermal physics, we would like want to get a better picture of the true like thermal structure of the gas, since this is very relevant for like fragmentation outcomes. We would like to include some protostellar feedback such as radiation and jets. We would like to have our simulations form these multiple systems to see like what is the effect of these like neighbor interactions. We want some detailed microphysics capable of describing this non-ideal magnetohydrodynamics. And at this point, this is quite difficult to figure out with like just pen and paper calculations and simple models. So this is why we'd like to turn to numerical simulations. And these aren't the first simulations of protostellar disk formation, but they are somewhat more sophisticated in a number of ways. So the first like big like disk population synthesis study was BATE in 2018. And this examined like, disk properties in a set of like hydrodynamic simulations with no feedback, like forming like almost like 200 protostars and just like looking at disk properties in this case. And then the first calculations, which included all of these non-ideal MHD effects, which are sometimes quite numerically challenging to implement, was Worcester et al. In 2019. So these included all three non-ideal effects, but again, no jet feedback, no radiative transfer in that sense. So in this work, we have a number of questions that we're trying to address. First of all is like, do we need non-ideal MHD in order to prevent this magnetic breaking catastrophe and form protostellar disks? We're also interested in how does protostellar jet feedback influence disk formation and evolution? And one of the questions going into this work was, how do multiple systems form? Like, can they form from disk fragmentation? And like, do the disks that we form, are they gravitationally unstable? So I will describe the numerical methods, which again is a combination of GIZMO, TurbSphere, and STARFORGE. So GIZMO is our gravity, radiation, MHD equation solver. It's a massively parallel multi-physics code. There's additional physics modules. Like in general, you can just solve the fluid equations in any context, but there's like specific modules developed for non-ideal MHD, for modeling dust physics in more detail, for modeling cosmic ray transport, and so on. And so what GIZMO does is it introduces these meshless finite mass volume partitioning methods for solving the equations. So some traditional like numerical methods include like SPH, where you kind of have like you're following like particle distributions, or you could have like grid codes where you're involving like fluxes through like cell boundaries. And so this is like a meshless method, which is intended to combine like the best advantages of both like mesh methods and SPH codes. There's an example, this is from the GIZMO user manual, but just showing that like relative to like grid codes, like this GIZMO is like meshless methods. They exhibit like superior angular momentum conservation. They don't have these issues with advection that are common with grid codes. And then compared to like SPH methods, you don't have to introduce like artificial viscosity or diffusion terms. So this is a comparison of like a 2D simulation of just like a rotating Keplerian disk. So in the top left panel, you have the initial conditions, and evolving this for many orbits, you would want to preserve these initial conditions. And so the top row shows the meshless finite mass and meshless finite volume methods after like 100 orbits. And then the lower row shows like how the smooth particle hydrodynamics of the stationary grid methods really decay over just a small number of orbits. And again, this is a very like idealized setup, and it's kind of like, you know, showing GIZMO in the best light and these other methods in the worst light. GIZMO is definitely not the only code that can model disk formation, but this is what we are using for our work. So yeah, again, some of the advantages of these MFM methods. Then TurbSphere, for this one, I have a video it'll play. So we want to have some like realistic turbulent initial conditions for our cloud. And we use this, we generate these turbulent conditions using this TurbSphere setup. So this video is just showing what that looks like. But essentially our calculations have two phases. We have our like stirring calculations and then our star forming calculations. So in our stirring calculations with TurbSphere, we don't have any self-gravity, so the gas can't collapse to form stars, but we confine the gas in like a roughly like localized, with like a potential to keep it localized, and we turbulently drive it as in like turbulent box simulations. So this helps us develop like, you know, nonlinear turbulence and a full turbulent cascade. And we do this for like a number of turbulent crossing times. And then we turn off the turbulent driving and start our star forming calculations where we turn on the self-gravity. And then finally, STARFORGE is stands for Star Formation in Gaseous Environments, and it's a numerical framework for modeling star formation, stellar feedback, and dynamics. So it basically describes how these, so one of the ways we reduce the computational cost of these calculations is we use sync particles. So we could, you know, in theory, continue like once the gas gets dense and starts collapsing, we could follow it through like the formation of like the first and second hydrostatic cores and, you know, actually like go down to the formation of the star. But again, you know, we're trying to span a wide range of scales in like temporal, spatial space, and it would be very computationally expensive to follow it down to that level of detail. So yeah, at a certain point, like at a critical density threshold and a number of other checks, we just replace the gas with a sync particle representing like an individual protostar. These follow like an evolutionary track like originally implemented in the Orion code. And these sync particles can also like accrete gas into like an accretion reservoir, and then this could be ejected as either like jet feedback or wind feedback. So this is all described in detail in the STARFORGE methods paper. So for this work, we are working with a set of 6 models. We are interested in comparing, you know, what are the disk formation outcomes with ideal versus non-ideal MHD, and then with no jet feedback versus using the subgrid like protostellar jet feedback implemented in STARFORGE. Something to note here is like when we were doing small scale tests at the current like mass resolution that we're using in this work, we don't observe any like self-consistently launched bipolar jets. These show up again as we increase the resolution, but like this resolution isn't attainable with our initial cloud size. So we really want to use this like subgrid feedback, since this protostellar jet feedback is likely like an important dynamical component of the model. So our 3 sets of MHD physics, we look at ideal MHD, and then non-ideal MHD, including only ohmic and bipolar resistivity, which are like the diffusive terms, and then also a set of models where we include the Hall effect. And this is partly because the Hall effect is the most numerically challenging to implement, owing to the fact that it can be like positive and negative. So there's like a number of works looking at non-ideal MHD and disk formation, which only include ohmic and bipolar. So we included a model like this to compare these works. And then so for each set of MHD physics, we have a model with and without subgrid feedback. I just have a table summarizing like some of the parameters of our models. I won't go into this in too much detail, but most relevant to note is the initial cloud size is, and I'm calling this a cloud, it really is not a full molecular cloud, but more like just like a subsection. But 50 solar masses for our cloud, radius of about 0.3 parsecs. We have an initial turbulent virial parameter of 1 and a mass to magnetic flux ratio of about 4. So it's gravitationally bound, the magnetic field isn't enough to overcome gravity and prevent gravitational collapse. We have our mass resolution where each like gas cell represents 10 to the minus 5 solar masses, and then a couple of parameters relevant for our MHD and jet feedback physics. And so one thing to note here is that like the non-ideal MHD resistivities are very sensitive to like the details of your dust model. And here we have a pretty simple case where we don't have like any like size distribution for our dust, like no like MRN distribution. We just assume like a single fixed grain size. And a single fixed cosmic ray ionization rate at the boundary of the cloud. And so we summarize also, so these models form anywhere from like 1 to 10 protostars and number of disks. Some of these are like single disks, some of these are like disks around binaries. Some of these like start out as single disks and become binary disks. The figure on the right here is showing just the star formation outcomes, so the mass of each sync particle that forms in our simulation. One thing to note here is that, so all the solid lines are sync particles formed in models without the subgrid jet feedback, and dashed lines are with the subgrid jet feedback. And you can see there's almost like an order of magnitude difference between the final stellar masses. So this jet feedback really is important for, we have like more fragmentation with jet feedback and lower overall final stellar masses, and this might have an influence on disk evolution. So going through some results that we see in this work, starting from like large scales and the turbulent driving calculations, going down to the disk formation outcomes. This is a video which is comparing the turb sphere calculations. On the left, we have the case with ideal MHD, and then on the right, we have with non-ideal MHD. And so something you can see here is that in the non-ideal case, the overall like cloud structure looks a lot smoother. So I'll let it play. And so this is something that's different from other works looking at like protostellar disk formation with non-ideal MHD, like some similar calculations, but without the feedback. Those works didn't see any differences in like the gas density or magnetic field structure up until you got to small scales, like less than like 0.01 parsecs. But something to note is that those works, they start with like a uniform sphere with like a prescribed like velocity field, so they don't actually do any like turbulent driving. And our results with this like turb sphere calculations are consistent with some like turbulent box simulations, which just included like ambipolar diffusion and look at the effect of including this on density magnetic field structures. And so these works found that like essentially ambipolar diffusion introduces this like ion neutral friction, which truncates the turbulent energy cascade down at smaller scales. Which led to like overall smoother density structures, magnetic field structures. And what we found in some of our tests is that, again, this ambipolar resistivity is very sensitive to like what we assume as our like dust grain size. So even like not talking about like a full distribution of sizes, but like a single dust grain size, our fiducial choice is this 0.1 microns in blue. And as we decrease the dust grain size, like the ambipolar resistivity really drops as a function of density. So this is behavior where, thinking about like potentials for future work, like this really doesn't capture like the dust physics all that well. And so this smoothing behavior, this is something we would like expect to actually see. It would be nice to get a sense of like what this would look like with a more realistic dust model.
But can I ask a quick question? There's no scale bar on the density there, so I'm just wondering, is this whole range shown where you expect ambipolar diffusion to be the dominant non-ideal term, or do you transition to the density regime where like Hall or resistivity would take over, and therefore the divergence, like how bad is the divergence with size? I'm wondering.
I can show the uncropped plot. Let's see.
Like there, yeah, the offset is much worse, obviously, at the high densities, but I'm just wondering, yeah. Just wonder where that is.
So
So I'm not trying to,
okay.
not trying to make you edit your talk mid-talk.
No worries. That's a good question. Yeah, I just like feel like sometimes these figures have very small axes labels. Yeah, so were you interested more in the density scaling?
Yeah, I guess, yeah, so right is, I can't,
Yeah, so this, I mean, I would say, yeah, this is more the low density ambient medium. This is also, I think this plot was generated from some of these like turb sphere calculations where we don't have self-gravity, so we're not actually like having any gravitational collapse happening. So yeah, I think this is representative of like the range of densities you would see in this figure.
see, but I guess I'm asking, so when you get to say 10 to, I think that's 10 to the 5 or 10 to the 6.
Yeah.
Is the ambipolar resistivity term still the dominant non-ideal
Yeah.
effect? Okay,
Yeah.
so all this whole range, even with that many order of magnitude divergence is still, okay.
Yeah.
So it is as, it's really, really bad, not just a little bad.
Yeah.
Okay.
Yeah, so we can also take a look at the magnetization of the cloud. And so this is consistent with previous works looking at ideal and non-ideal MHD, where at the densities that we see in our cloud, there's not really a difference in the magnetic field strength between the ideal and the non-ideal MHD models. The magnetic field strength generally follows like b to the rho as like root of the 1/2 within our density range of interest here. We can take a look at the values of our non-ideal coefficient or resistivities. So yeah, I have this in mass density, not number density, but I think this kind of gives you a sense of where which effect dominates. So for most of the gas, ambipolar really is the dominant effect. Our like disk densities, like I have a slide with our criteria for like identifying disk material, but one of the criteria is a number density of like 10 to the yeah, I think a mass density, I would say like right here where this like 10 to the minus 14 rho, that's about where like our like disk densities begin. But yeah, anyway, this is mostly to show, I mean, this is the first time that these like non-ideal coefficients have been studied in detail in GIZMO. And so these values are pretty consistent with other codes. This is the figure I showed before, and here I have a video. So this will be showing kind of the effects of the protostellar jet feedback on the evolution of the cloud. So the top row is the projected surface density, and then the bottom row is the line of sight, like 1D velocity dispersion. And our left column is our like full non-ideal MHD model with ohmic, ambipolar, and Hall, but no jet feedback. And then the right is with jet feedback. So you'll see in the right column, the jet feedback is quite dramatic. So what we see also in the figure on the left, which is showing, yeah, like the masses of all the protostars that form. Again, so the models without jets are solid lines. So these models, each like counterpart with jet feedback forms more stars. So there's more fragmentation happening, and then the final stellar masses are lower overall. And you might also guess, just seeing from like how like chaotic that jet feedback is, that might like affect the disks as well. So talking, yeah.
Question about the previous figure. What, so on the left, it starts at 0.4 million years. Is that taking into account the turb sphere calculation? Or?
Good question. Yeah, so this is from the start of the star forming calculations. So we do turb sphere for like 3 turbulent crossing times, which is similar to 0.4 million years. And then we start the star forming calculations. So from the start of the star forming calculations, these stars start forming like roughly about like 1 free fall time, which is also about like 0.4 million years for our clouds. Yeah, so how do we identify these disks? Yeah, because this is like with the simulations, like this is very different from the picture of an observer would have. We have like the full 3D information of like all the gas in our simulations. But essentially, we use a number of criteria like that are the same as some other works studying disk formation. We have a density threshold of number density greater than 10 to the 9. We check the different like velocity components in like a cylindrical coordinate system centered at the disk center of mass to see that it's like in more or less Keplerian rotation, hydrostatic equilibrium, and then we also check to see that like rotational support exceeds the thermal support. So the figure below is kind of this is from some earlier tests we were doing. This model doesn't have any like radiation feedback from the protostar, so it's a very like cold thin disk. But the like little inset figures kind of show like this is what our algorithm picks up as the disk material. And so we see that more or less disks form in all of our models. The top left plot is the binary disk that forms in our ideal MHD model. The rest of these are the non-ideal models. We have some like single disks and binary disks. You can see some like what could be like spiral arms or maybe even streamers. Yeah, that's the gas density through the disk midplane. This is just looking at the structure of the magnetic field of these disks. So you can see that it really does follow the rotation. It's mostly just some cool pictures to show. And so we form disks in all of our models according to like this like disk identification criteria. But there is this notable exception of like this quadruple disk that forms in the ideal MHD model with jet feedback, which is the top row in this figure. It's just the gas density projected along 3 different axes. And for comparison, I'm showing like the 2 binary disks that form in the non-ideal model with no jet feedback. So you can see the surface density is a lot lower in the ideal case. And so with the small number of disks that we form in our models, like, 1 to 2 to 3, it's hard to give any like, make any statistical statements about like differences in disk properties between ideal and non-ideal MHD, but this does suggest that like either ideal MHD or possibly this like jet feedback is disruptive to disk formation. This is one of the issues of using like a subgrid model for the protostellar jets is we do think that like, the picture between like the disk behavior, the accretion, and like the outflowing jets should be, linked on some sense. And here, like our subgrid prescription basically just launches jets whenever. And again, so we have like the different criteria for identifying disk material, but all the plots I'll show about like disk properties are only considering like kind of long-lived disks that last for like 100 to like a couple hundred kiloyears. During our disk identification procedure, we identify some disks that like exist for like a single snapshot or 2, which is like 6 to 12 kiloyears in our simulations. But these jets are like quickly disrupted either by like interaction with neighbors or this jet feedback. So, this either suggests that we might want to have like a more detailed jet feedback model, or again, we might want to have like a larger study to get like some statistical statements about whether like ideal MHD or jet feedback is more disruptive. Yeah, so looking at some of like properties or disk properties in these simulations, again, the disks that I'll show in these plots are like disks that persist for a couple of hundred kiloyears, and this is quite a bit longer than some like previous studies of disk formation. So just to go through how to read these plots, the different columns are like our different sets of MHD physics from ideal to your most complicated non-ideal model. And then the 2 rows, the top row is with no jet feedback, and the bottom row is with jet feedback. So I'll talk through just like some specific cases here. Also, we don't really quantify like how well resolved our disks are here in case of like some kind of like Jeans criterion. But just to give a sense, these like red shaded regions show like when the disk contains like less than 100 or like even less than 10 cells. So again, these are like picked up as disks by our like algorithm, but hard to make any like trustworthy statements about disk properties here. And the ideal MHD plus jets disk is the one in the bottom left. And so this one like, almost never has more than like 100 cells. So we don't really, we can't really like consider its properties. There's also a suggestion that maybe the ideal MHD disk lifetime is a bit shorter. So here I have a video of just what this ideal MHD model looks like. The model with ohmic resistivity and bipolar diffusion, this one only forms a single star. And it's a very massive star by the end of the simulation, like, larger than we would expect for low mass star formation calculations. It also has the most massive disk. Its counterpart with jet feedback, once you introduce jet feedback, you form 5 protostars instead of 1. You see like a lot more volatility in like the disk mass at later times as jet feedback from the neighbors disrupts the disk. The model with ohmic resistivity and bipolar diffusion and the Hall effect is interesting because it forms these two interacting binaries, and the binary disks have similar masses, and also like both components in the binary are very similar in mass, stars. So we're thinking it might be interesting to do like a larger study where we look more closely at how like disks do affect binary evolution. I have a video of this model as well, a little bit more exciting. And then finally, our model with all 3 non-ideal effects and and with jet feedback. This is like has the most chaotic feedback, as you'll see in the next movie. It forms the most stars, 10. And we also have this interesting behavior where there's like this like single disk that forms at like earlier times. There's a number of disks that like survive only for like a snapshot or 2 before being disrupted. But then once kind of this like chaotic initial like star forming behavior has calmed down, we also form this quite long-lasting, pretty stable binary disk at later times. And this is like from material that's accreted not from the needle envelope, but from later stage in falling gas. So you'll see that in this movie. And then we form this like binary disk at later times. We take a look at like disk radii here in our simulations. Here we define the disk radius as radius containing like 63.2% of the total disk mass. This is based on some like surface density profiles used in observations. Again, I can't like really give you like a definitive answer, like, like here's the mean disk radius because we have a very small sample, but generally the radius ranges from between like a few 10 to a few 100 AU, which is more or less consistent with observed disks. We take a look at the disk aspect ratio, where here we define it as like the ratio between the minimum and the maximum eigenvalues of this the matrix, basically like of like positions relative to the center of mass. So this is again probably different from how you would define the aspect ratio in observations. There's a postdoc in Stella's group, Cheng Han, who is more interested in like comparing aspect ratios in simulated versus observed disks. So I think he would have more information on that. But in general, we see this aspect ratio tends to decrease with time for most of these disks. By then it's somewhere below like 0.2 or so. We take a look at the disk to stellar mass ratio, which also tends to decrease over time. Yeah, you would expect self-gravity to become important roughly when this ratio is greater than like 1 to 100. So that's what this like red shaded region indicates here. So this massive disk that forms in the model with ohmic and ambipolar but no jet feedback really is within that range for quite a long time, but we do some more stability analysis and we don't see any fragmentation here. So yeah, another way we look at the stability of this disk is by looking at the tumor cube parameter. Here CS is the sound speed, K is the epicyclic frequency, which for our disks we assume to be just the Keplerian like angular velocity, pi g surface density. And so we would generally expect that like disks are stable when Q is large, and as Q approaches 1, they become more unstable. In this regime of like 1 to 2, you might see some spiral wave development. And so we make some plots of this tumor cube parameter for some of our disks. So this is the binary disk that forms in the ideal MHD model. Yeah, the bottom row, we don't really see any regions where like Q is below 2. This is just comparing like different stages of the disk's evolution. This is the same plot for that massive disk that forms in the model with ohmic resistivity and bipolar diffusion. So this one, there are some regions where like Q is in the like 1 to 2 range, and we do see like a lot more spiral structure, but we don't see any like, there's no disk fragmentation occurring in any of our models. And part of this could be an issue with our numerical resolution, like this mass resolution of 10 to the minus 5. It's the highest resolution used in STARFORGE calculations, but it's still, you know, there's room to push it down further. We take a look at the evolution between the like the stellar spin axis and the rotation axis of the disk. And we see that these like the disk spins are generally well aligned with the stellar spin, so maybe between like below like 40 to like 20 degrees misalignment. Yeah. And we also take a look at the relative orientation between like the disk rotation axis and the like direction of the like the local magnetic field, which we define to be the local field like averaged over like a 1000 AU sphere. Because if you recall like some potential resolutions to the magnetic braking catastrophe, there's the idea that like introducing misalignment might help with alleviate magnetic braking. There's some studies suggesting that, yeah, like these models without the Hall effect, there's a lot of scatter. Most of this variability is like fluctuations in the direction of the magnetic field, not the disk rotation. But you could maybe argue that they're generally like scattered around like an angle of 90 degrees perpendicular. But these Hall models show a very like clear sign and behavior of like becoming anti-aligned with the local magnetic field with time. And this is consistent with like 2D calculations of Zhao et al. In like 2020, where they looked at like the effect of including the Hall effect in these like protostellar disk calculations, because as I mentioned earlier, there's this suggestion that there might be like a bimodality in like disk properties, like with and without the Hall effect, depending on whether like the magnetic field and the spin is aligned or anti-aligned. But the Zhao et al. 2020 paper basically said that this is a transient effect that's mostly relevant in the first like couple 10,000 years of disk evolution. And at later times, like when disks form in the Hall models, they generally end up becoming anti-aligned with the local magnetic field. So it's interesting to see that we also observe this in our simulations. Yeah, I think it's the final one of these plots, but we also see that the stars which do have disks are the most massive by the end of the calculations. So here, instead of showing the disk mass, the colored lines are representing the masses of the stars that form in that simulation. And then like the black, gray, solid regions is the part of the stellar lifetime during which there's like a disk, as is picked up by our algorithm. So again, on one hand, like, you know, disks regulate the accretion of material to the stars. So you could think that this is, you know, an effect of like, if the star has a disk, it's accreting more material. Or it also could be a consequence of like, you know, more massive stars are more likely to have disks in our simulations. It's possible that like, you know, smaller disks are just not resolved in our simulations. Also like some of these like dotted lines, these are like stars that like never have a disk. And a lot of these are like low mass stars that are like ejected into low density ambient medium like very early on. So they don't really have a lot of material to accrete disks from. And yeah, going back to the point, we see that these are just slices through the disk midplane of showing some of these like non-ideal coefficients throughout the midplane. Ohmic resistivity, most efficient in the densest central regions, and bipolar resistivity or diffusion, more in like the surrounding gas. And the Hall effect is the dominant effect throughout most of the disk in our models. So to summarize these results, we see that during the turb sphere calculations, non-ideal MHD does cause like smoother density structures. And this is again, very sensitive to the choice of dust grain size. We see that disks, at least as like defined by our selection criteria, form in all of the models. The disk masses and radii are broadly consistent with observed disks. We would need to do like a population study to get better statistics. The disks tend to be relatively well aligned with the stellar angular momentum axis, within like 20 degrees or so, and have an aspect ratio which is fairly small. And we also see that in models with the Hall effect, the disk spins tend to become anti-aligned with the local magnetic field direction. And no disk fragmentation is observed. The effect of including jet feedback seems to be that it increases fragmentation and lowers the final stellar masses. It does seem to be somewhat disruptive to disk formations. So yeah, one of the avenues for future work that I'm considering is trying to like maybe refine our like subgrid jet feedback model. And just a few directions for future work. So one avenue is perhaps considering some more detailed non-ideal MHD microphysics. So, you know, we're making a lot of simplifying assumptions here. We're using like a single like dust grain size, fixed like dust to gas ratio. We don't have any evolution of dust properties like due to like shattering, coagulation, no like grain destruction or growth. We're also like, yeah, we don't like capture any like, you know, radial drift or like settling of dust within the disk, which would be very relevant for, you know, the relative importance of these non-ideal effects throughout the disk. And we're also assuming just like a fixed cosmic ray ionization rate at the boundary of our cloud, and we don't include any cosmic ray transport. And there's like some recent works that really suggest that like, you know, cosmic rays could be like produced right at the protostellar surface and so on. So this also would affect the microphysics governing the resistivities. But before getting into like more detailed like physics models, there's also a recent paper that came out last year on arXiv that there might be more fundamental issues with the non-ideal MHD assumptions themselves. And this has to do with this issue of superthermal drift corrections. And so non-ideal MHD approximations, they can lead to very like steep magnetic gradients, particularly with the Hall effect. And this causes like drift velocities between different charged species to exceed the thermal speeds. This invalidates like a lot of the assumptions used to derive the non-ideal MHD equations. For example, like the collision rates that go into the calculation of the non-ideal resistivities assume that there's like negligible drift velocities. So in this like standard picture, yeah, like here, it's kind of like a plot showing like which effect is most important. The x-axis is density and the y-axis is the magnetic field strength. So you have like ambipolar diffusion dominating at like low densities, omega high densities, and then in kind of the disk regime, you have the Hall effect. But once you correct for these like superthermal drifts that might be possible, the net effect of all of this is to essentially like eliminate the Hall regime. You end up with like instabilities in the plasma, which tend to like smooth out these steep gradients. And the overall effect is to like introduce this like so-called like anomalous resistivity and slightly decrease the value of the ambipolar resistivity, but like greatly boost ohmic resistivity at high densities. So if these superthermal drift corrections, they haven't really been studied in like astrophysical context before, but they are known in like more like plasma physics. So again, before like we try to like do like detailed modeling of like dust and like cosmic ray ionization transport and so on, it might be worth considering whether like, you know, whether these resistivities as we calculate them are very physical. Yeah, so I will leave my conclusion slide up here and I'm happy to take any questions.
Questions? For people online, if you have any questions, you can raise your hand or type your questions in the chat.
Sure. Very nice talk, very interesting. So I just have two questions. So in the previous slides where you compare your code, like you said, when you include these non-ideal MHD effects, you get smoother structure compared to other codes. I wonder if you use like the same coefficients as the other codes, and what's your, for example, what's your numerical resistivity?
Right, yeah, so the works I was talking about that didn't see this like smoothing, in terms of the same coefficients, so like there's a NICEL library that's used for like a lot of the SVH calculations that like pre-computes these resistivities. But like they have figures showing like what the values of their resistivities are as like a function of density, similar to like this figure here. And so actually, yeah, I think that's the plot I included here. Like this. So broadly, like the way we calculate the resistivities are somewhat different, but like the values that they give for like our like densities and temperatures, magnetic field strengths are comparable. So I think the main difference really is this turbulent driving phase, which our calculations include, and these other disk formation studies, they just go straight to the star forming calculations. No turbulent driving.
And sorry, the second question, you said there's no disk fragmentation in your simulation, but I
Yeah.
see you have like binaries or multiple system in your simulation. So those
Yeah.
are from initial fragmentation, either
Yeah.
bound or captured later.
Yeah, we don't really see a lot of capture. There's more detail in the paper, which will hopefully be accepted soon. But we mostly see like core and filament fragmentation. Actually, there is quite an interesting system we see, which relates to the point I made about like our density cutoff for disk identification. So this is our model where this is with ohmic and bipolar, and it forms two initial sync particles, and then there's like this rotating like envelope structure, and this extends out to like a couple like 1,000 AU, so like a lot bigger than we would typically like call a disk. But this structure like fragments to form like 3 additional stars. And we took a look at like here's like a plot of like the surface density and the tumor Q, and so this one is quite unstable all throughout like this region. And it is in like more or less Keplerian rotation, which is interesting. So
why don't you call that disk fragmentation?
So this is because this material is not identified as a disk based on our density
Oh, okay,
threshold.
so
So it does seem that like what we call like the rotating envelope, the disk, like these structures are like much more like continuous rather than like these like discrete objects that we would like to call them. But this is something we're interested in working with Ching Han and Stella's group and seeing if this is something we could observe potentially. So I guess it is a question of like, what do we call a disk?
Nama, do you want to ask your question yourself?
Yeah, sure. Nina, thanks for a great talk. I was wondering that nearly half of the jets are observed to be asymmetric in nature. So you have one lobe that is longer or brighter and the other is shorter or dimmer. And generally Hall effect, or recently at least, is thought to be responsible for that. Do you see those forming in your simulations, and can you comment on like how they form?
Yeah, so all of the jet feedback that we have in these simulations. So like I said, we don't observe any like self-consistently launched jets, but we do see like some kind of like bipolar outflow. I don't know about the figures, I'm just trying to find it here. Let me zoom in. So in our ideal MHD model, we do get this like lower velocity self-consistently launched outflow. You can kind of see the bow shocks in this figure, just showing the time evolution. And this one is asymmetric with like one lobe larger than the other. This, however, is a model with ideal MHD, so no Hall effect. But yeah, so we would expect like protostellar jet velocities to be like 10 to 100 kilometers per second. This is like more like 5 at most. But yeah, so to answer your question, like any of the jets like in the talk, that's all like subgrid feedback, and so that has like no knowledge of like the MHD physics. It's just like a simple numerical like prescription, like the sync particle accretes mass and then just launches it in with equal and opposite like momentum in opposite directions.
So do you understand why the jets are triggering more fragmentation? I understand why they would reduce the overall masses just by decreasing efficiency, but how are they making more stars?
Good question. Yeah, so I mean, on one hand, they do reduce overall efficiency and like the stellar masses. So there is like lower luminosities, so the temperature is lower, which could increase fragmentation. But also just these jets, they're like compressing nearby material and maybe like triggering like more bursts of star formation. Like I think this slide, this is the non-ideal model. This is like where like we have like a number of sync particles forming like along a filament. You can see like somewhat more like structure in the bottom row that has the jet feedback. So I think it's a combination of like lower luminosities and like lower temperature, some more fragmentation, but also this like extra like compression from the jets,
I see, I guess the jets are just inserting mechanical energy,
as opposed to.
thermal energy. There's no means by which the jet's mechanical energy gets transferred to heat. Because you might think that jets could also help heat the gas,
That's a good point. Yeah.
but if they're just imparting momentum, then obviously that won't happen.
They're just imparting mechanical energy.
So here I remind people that we're at the top of the hour, but we still have this room until 1:15, and people can stay. Feel free to leave. You have to, and we can still continue our discussion here.
Can I just say, before everybody leaves, there's still spots on Nina's schedule if you want to sign up. She'll be here through Wednesday.
Yeah, I would love to talk to you.
And Serena, do you want to ask your question?
Yeah, I have a question. Yeah, this figure actually that's a bar is a 2000 AU, right? I actually see, we see them in like in Orion, in filamentary area, molecular cloud, a lot of jets, very young. We don't, the age, assuming they are younger than 500,000 years or younger. And I see that their jets actually are lined with, maybe there's a projection to another disks, basically. There are multiple jets and they are like pointing to each other. In that case, do you have such cases in your sample? I wonder if they would actually be destroying the other jets if they're close enough, and how close enough they should be in order to actually affect the other disk system with jets.
Yeah, that's a good question. I think in these simulations, we don't really see that because, yeah, we're forming anywhere from like 1 to 10 protostars, and they all send like, aside for the ones that get like dynamically ejected, they're all kind of like in the same like gravitational potential well. So like in this jet feedback, like all the stars are kind of like in a single system, and like you see the jets like extending out from the system. So this is another reason why it would maybe be interesting to start with like a larger initial cloud, like maybe like 2000 or 200 to like 500 solar masses, where form like kind of like distinct multiple systems. Then we could see, how maybe like these like interacting jets would affect the evolution. So yeah, we don't see these in these simulations, but it would be interesting to consider.
Yeah, thanks.
Sorry, one more question. When you say the jet increased fragmentation, do you mean, I can't see really, is it those fragmentation along the jet or near the jet, or?
So this is, the models, these models, the only difference between the top and the bottom row is like with or without this like subgrid jet feedback. So this is at the same point in their evolution. So this top model has formed like these like 4 stars, and that's like the 4 total stars that form here. This one has formed like 6 out of its eventual like 10 protostars, but they all mostly like form along this filament. So yeah, I
That
guess.
filament is not the jet, that's the filament.
Yeah, the filament, the jet.
So can we see any jets in that plot?
You can see, so like right here, this like horizontal structure, this is kind of the jet. They're much more visible in velocity space. There's a little bit of like a bow shock here from, there's a jet coming out in this figure. Yeah, I have an image with the velocity dispersion, but it's not just at hand here.
I remember in one of the cartoons you showed the jet is quite obvious compared to the blue jet.
Yes.
And also it's also like the asymmetric jet. Any other questions from online audience?
I have, yeah, sure. So in the 6-panel figure, where you have ideal, non-ideal Hall effect with jet, without jet.
Like these 6-panel figures?
Yeah,
Mhm.
I was wondering about the disk lifetime. Like it looked like some disks are transient, like in the first million years they come and go. Does that mean some stars form without disk? And are you sure that these disks that form at the end will continue to be disks?
Yeah, I mean, so we evolve our models for like different amounts of time, but mostly until like most of like the gas near the star forming region has been dispersed and like the disk is gone. This like non-ideal model with all the effects plus jets, like there's still a disk at the end of our calculations, but it is dropping in mass. So I guess for most of the disks that form, they form like relatively soon after the component protostars, like maybe within like a few, like within 100, like 50 to 100,000 years. Yeah, the question of like, do most of these stars form without disks? Again, we're not capable of resolving like the smallest disks in our simulations, so I'd be like a little hesitant to like answer that. It would be nice to like do a study with higher numerical resolution and capture these small disks. But you were asking also like, how can we be sure that these disks last?
Right.
Again, so with the exception of like this model, like these, like most of the disks, like at this point, like we're not picking up a disk with our disk detection algorithm. And yeah, they typically in our simulations last for like 100 to 300,000 years after formation. There is kind of like, I mean, when I talk about there's like a couple of disks that like appear for like a snapshot or two. So our snapshot time spacing is like 6,000 years. It's usually like, either disks form and are disrupted very quickly, or they're these like disks that like live for like at least 100,000 years. There's not really like an in-between population.
Any other questions? If not, let's thank our speaker again.
If anyone else wants to join for lunch, I think at least Shua and I are gonna go out.